We're going to take the alkylation another step further and look at being able to form kinetic and thermodynamic enolates. These are terms you should be familiar with. When we're talking about kinetic products, we're thinking about what's formed faster. When we're talking about thermodynamic products, we're thinking about what's overall the most stable. So kinetics is about speed, thermodynamics is about stability. As far as enolates go, this is really only a concern when you have two different enolizable positions. Let's go back to a molecule that we looked at earlier in this chapter. This, 2-methylcyclopentanone. We saw that we could form two enols with this. We could form an enol with one of these protons, or we could form an enol with this proton. So we'll talk about the whys in a second, but if we use a weaker base like sodium ethoxide, and usually when you use a base like sodium ethoxide, it's accompanied by the corresponding alcohol, which will be ethanol. That's not a super strong base, so this is an equilibrium process, and we do this at room temperature. When you use that as a base, we're going to form the enolate on the side of the red proton. And this is called the thermodynamic enolate. Okay, on the other hand, if you use that strong bulky base that we talked about, LDA, when we use LDA, a lot of times you'll see the solvent written, which is usually THF, and this is done at low temperatures. Most kinetic reactions are done at low temperatures, minus 78 degrees. In this case, we end up forming the enolate on the other side. And this is the kinetic enolate. So we want to think about why we get these particular products under these particular conditions. This kinetic product, let's start with it. It's the less substituted double bond. Okay, just to review double bond substitution, this double bond has 1, 2, 3 non-hydrogen groups attached to it. That's tri-substituted. Okay, the other double bond in the thermodynamic product has 1, 2, 3, 4 non-hydrogen groups attached to it. It's tetrasubstituted. So in the kinetic enolate, the less substituted double bond forms faster. But the reason for that is just a steric argument. We have a bulky base which is LDA, and of these two sides, this right-hand side is more substituted, it's hindered by this methyl group, it's less accessible. Versus this side, we have these two small hydrogen that's more accessible. So it attacks some more accessible hydrogens preferentially. So that would be those two hydrogen there. So it reacts with those hydrogen faster to form this kinetic enolate, and then below temperature prevents a reverse reaction. So we can stop this and form 100% of this kinetic enolate. And you'll notice I used this single arrow to say that 100% of the carbonyl compound is converted to 100% enolate with this strong base. With the thermodynamic conditions, on the other hand, we have equilibrium arrows. We're using a weaker base, which doesn't just immediately convert all of the carbonyl into enolate. What happens is this weak base might react with one of these hydrogen, it might react with this hydrogen to form an enolate. But at room temperature, this is reversible. And over time, equilibrium is going to favor the overall more stable enolate. And we know that this tetrasubstituted double bond is overall more stable than a trisubstituted double bond. And here this equilibrium is going to favor the overall more stable enolate, which is this one. So we can choose whichever base we want to give us the enolate that's desired. And then in a second step, we can add our organohalide to alkylate either of these. So let's look at a couple of examples of that. So let's try these two problems here. The first one, we use LDA as a base, followed by this allylic iodide as our organohalide. The second one, we use sodium methoxide as the base, followed by methyl iodide. So I would encourage you to pause the video and see if you can draw the correct products, and then you can play it to see the answers. The first thing we want to do is identify what kind of enolate you're going to form. With LDA, we're going to form the kinetic enolate. That's going to be at this less substituted alpha carbon. Here would be the resonance form for the kinetic enolate where the negative charge is on the carbon. That will then react with the organohalide. Giving us the product where we have these three carbons bonded to the alpha position. So there's 1, 2, and 3. And our second reaction we have the conditions for the thermodynamic enolate. That's going to form the enolate at this carbon. So if we draw that enolate, and again, we'll do the one where the resonance structure has the negative charge on the carbon, we get this. That will react with the iodomethane. And here we're just adding a second methyl group to the alpha carbon.